Okay, good day everyone, and let's see if this is working. And if this is working, then we can get going. But wait, okay, I can see that it's working. Let me know if you don't hear me. I guess you are going to anyway. Welcome to my live stream. I'm Gynvael, and today's moderator is KrzaQ, whose nickname you can see here. This is how you actually write KrzaQ. And if you have any questions, then I actually should open my portal where I will be able to see your questions. Otherwise, it might not work too well. Okay, oh, no, this is weird. Perfect. Okay, so yeah, if you have any questions, you have to ping KrzaQ either on YouTube chat, Discord, on IRC, wherever you are at the moment, and KrzaQ will pass the question to me, so I will be able to answer the question during the live stream. That's basically how it works. Yeah, if you ping me, then I will not be able to see the question, because, well, I might, if I'm actually luckily looking at the chat at the moment. Cool. Now, today's topic is going to be basically a continuation of last week's topic, which was trying to solve some challenges, or actually the challenges I've made from Dragon CTF teaser, which took place 2 weekends ago, I believe. And we did go through two easy challenges, and then we were going through the last challenge, which was a reverse engineering challenge rated easy or hard, well, sorry, not easy, medium to hard, more on the hard side. The challenge was about this little thing here, which is an, here we go, come on, yeah. Okay, yeah, I guess you could see something. I need to work on that, I guess. Anyway, which is basically a custom FPU based on a PIC microcontroller, and you can connect it to Arduino or whatever else. And the challenge was that you got Arduino code, and you were able to, which actually, you get the code, so you could read it without any reverse engineering, and the code was uploading and writing to the EEPROM of this FPU, like custom bytecode or whatever. And we basically had to reverse engineer the bytecode. And the state we finished last time was basically we had started writing a disassembler, and we had some disassembler already written down, and we could analyze 1 or 2 or 3 small functions, but not larger functions. And I think we discovered self-modifying code here and there. So today we are going to continue writing the disassembler and trying to do something about that self-modifying code which we discovered. That's basically it. Some Polish text on your t-shirt, yeah. It says, it's from Baldur's Gate. You must gather your party before venturing forth. I think that's the English version. Cool. So let's chat about who's the... Well, about, you know, standard stuff which I talk while waiting for people to show up. Meaning, today's moderator is, as mentioned, KrzaQ, and I cannot zoom in. Okay, why cannot I zoom in? I'm sorry. Windows had an update, and after Windows update, my zoom in program stopped executing itself while Windows is booting. Perfect. Now, here we go. Okay, so KrzaQ is today's moderator, and you can visit his website, though I'm not claiming it's frequently updated, but there's a lot of interesting stuff there anyway. Cool. Now, the CTF itself, I think the website is still available at ctf.dragonsector.pl. Yeah, it's still available, and if I sign in, can I sign in? I can sign in. Yeah, the challenges are still here, at least some of them. So I'll give you this. Okay, and we will look at we are basically trying to solve this challenge, this one here, ummmfpu. Because, like, well, it's not it's like ummmfpu, actually, that what the chip is being called, and is actually micro mega, because that's the name of the corporation which created it. Corporation is a company, I'm not sure it's actually a corporation. Anyway, yeah, so we will be continuing it. Now, before we get there, let's do some random updates. First, page layout. You know, the first issue is out. It's still beta. I see the question on the chat, like, when will beta 1 turn into something else? Good question. Hopefully this week it will turn to beta. Oh, no, maybe it will take a few more days. But basically, beta 2 will be fixed menus, but also the print versions. And then there will be beta 3, which will be the type of PDFs, which it will be final basically. It will be a PDF which is also compatible with screen readers and has some more bugs fixed, and like with all the new additions, new issues, we will only issue the final version without going through the betas as we are going now. I believe we actually have like more. We have 40 articles in review, 2 already ready. A couple of them are actually like almost finished, so we are about here. We are slowly going through the review. The deadline for submissions, if you are interested to write something for us, it's in 11 days. So you still have 11 days to send something. After that deadline, it might be tricky to get it in. Do remember that we are also accepting community ads, meaning free advertisement of your free projects, which are created for community, from the goodness of one's heart. It's like projects, tutorials, tools, whatever. It does have to be free without any strings attached, basically. And then we can make a half-page advertisement for you, just as we did in the first issue. So we are also accepting that. I don't think we received even one so far. So you might want to, yeah, like you can send us ads, basically, like free ads, and we'll put them in. This is how an ad looks like. Wait, I'm pretty sure we have an ad. Yeah, for example, this is a community advertisement of a pretty cool podcast by DevNull. Here you go. And on the same page, there's another community advertisement. If your company would like to buy an advertisement, you can also look at this ads page and look at the sponsorship ads section. Thank you in advance. Now, I guess we did like 3 live streams ago. We went through my bookcases, bookcases which are there, right? Only through IT books on the bookcases, and it still took 2 hours. Now I updated my bookcases with a couple of more books. This is one of them, Undocumented Windows, and this is about, yes, covers Windows 3.1 and 3.0. This is a pretty old, pretty large book about the like secrets inside Windows 3.0. Then I also got Dissecting DOS book. A code level look at the DOS operating system. Here's the author. Wow, it's Michael Podanowski. Okay, that sounds like a Polish name, but it's not written in a Polish fashion. It's not super thick, it's not thin either. And another one, which is also about DOS. It's Extending DOS, a Programmer's Guide to Protected Mode DOS. And here are the authors, quite a lot of them, actually quite a lot of pretty known names too. This is about how to run like 32-bit applications in the 16-bit operating system, which is DOS. In the late era of DOS, most games were basically 32-bit applications. So you did it like this, but on DOS you run a DOS extender, for example, DOS GW4 or 4GW, and that basically switched into 32 bits, set up the segments in whatever way, or paging or whatever, and then loaded the game into that, and the game operated in 32 bits, still making some system calls to BIOS or to DOS through an interface switching back to 16 mode, executing the interrupt, like the API in BIOS or an API in DOS, and then going back to 32 bits to continue the gameplay. That was quite popular, actually. Weird choice of fuel for the fireplace. No, it's... oh my, how could you? Yeah. Perfect. I think I ran out of things to say, so we can get started with the... Yes, I believe we can... Oh wow, I see I have captions, automatic captions turned on YouTube. That's interesting. Yeah, I wonder how close that is to what I'm actually saying. Anyway, I guess we can get going with the challenge itself, and let me find the directory. Okay, here we go, and we can take a look what was the state we had it at last time. I do believe you remember the screenshot from last time. It's basically the well, the interface of a challenge. If you would have an Arduino and this chip connected, then if you launch it, you would see something like this. I provided the screenshot to the players so they actually know what to look at. And that wasn't a huge giveaway because you actually also got the source code for Arduino, which I don't think oh no, here it is, here we go. Yeah, which we did go through last time, and just a quick recap. There's almost nothing here. There's like this large EEPROM upload, which basically grabs a slot in the EEPROM memory, in the like read-only memory, which we are writing to, so that's not like really read-only memory. But yeah, it's non-volatile anyway. So it's a function which writes into EEPROM, and then this main function basically asks for the flag, and before it asks for the flag, it uploads the bytecode into the EEPROM of the FPU. After that's done, it asks for the flag, and then it puts the flag, it sends the flag using this strset function method opcode, let's call it opcode maybe, to the FPU, and then it calls start slot. It calls a function in the bytecode on the FPU and waits until the FPU finishes processing. FPU being here floating point unit, you can treat like an external accelerator for Arduino to do 32-bit math. And then it says like grabs a string from which is returned by the FPU, and it writes it, sends it to Arduino, which we I guess saw on the screenshot as well. Yeah, like this is sent by the FPU to the Arduino, and Arduino sends it through the COM interface to the monitor. And we started analyzing the bytecode. The bytecode looks like this, which I guess isn't super readable. We know that the start slot is 0, and the way the slots were actually, or the EEPROM is divided. This EEPROM has, I believe, like this amount of bytes of memory, not a lot, 1 kilobyte, but that's a lot for like this challenge, right? Quite a lot actually. Way more than needed. Well, maybe not way more, but more than needed. The bytecode is smaller than that. That's also good news for us. Now, the addressing is actually per 4 bytes. So each slot, or like each address slot, if you will, is 4 bytes. Yeah. Maybe like this. Alright, 4 bytes, yeah. And we know that the format of each function inside was first a byte which says what's the length of a function, so like the length, and then the bytecode, and it has to end with the return opcode. That's basically required by the FPU. And yeah, like if a function on a slot would be if a function would be uploaded to some slot, the first byte would be the length of the function, then the bytecode, and then the ret. And we, I think, determined that there are 12 functions or something like that. We started writing the disassembler. We made this opcodes thing for us, where we basically noted that this is the selecta opcode, and it accepts one argument, which is a register, and we got this information. This isn't fully filled. We got the opcodes from the manufacturer's published headers for whatever, like SDK, right? And we got whatever arguments are required here from the documentation. And I guess it would be a good idea to open the documentation because we will be using it again. So ummmfpu, this version, and yeah, this is the website of the corporation, and here's the datasheet and instructions set. The players were kinda expected to read the datasheet and the instruction set. I did read it. We are not going to read it online. There are actually a couple of them for the instruction set, because there are like 2 more instruction sets which are not in the, actually 3 more instruction sets which are not part of the basic instruction set. These are basically matrix operations. I think this is actually, I thought this was part of the original instruction set, and there are also Fourier transform instructions, which we do not care about. Now, again, to basically repeat what we already said last time, this machine has 127 32-bit registers. It doesn't have any RAM memory, it doesn't have any random access memory, which is weird, but like with 127 registers, that's fine. It does have EEPROM from which it can read, to which it could write. There's also flash memory, I think like 3 kilobytes of flash memory, from which it can read, but it cannot write back to it. And there are some temporary registers, like these are like similar to these 32-bit general purpose registers. These are actually either floating point or long integers, basically. And apart from that, what is not written here, but maybe, I don't think we'll actually find it. Okay, anyway, there are two more registers, which is A and X, and these are only symlinks, like aliases to whatever registers. And we can set, like we can tell that we want A to point to register 1, but later on we can say I want A now to point to register 127. And there's this instruction select A, which does it. So we have to remember that register X and register A are actually aliases to whatever registers we selected. Which works kinda like, yeah, like this whole register set kinda behaves like RAM, I would say, on its own. Because you can do that. Now, there's one more funny register, which is, I'm not sure if it's fully described here, but it will be important to what we will be looking at soon. And to intro you into that register, we will look at the instruction, again on the Arduino code, sorry. Here's the Arduino code, which is uploading the flag, and I said the upload of a flag is done with this opcode, right? So let's look for this in the manual, in the, not datasheet, but instruction set. And this is copy string to string buffer. So there is such a thing as string buffer. Apart from the registers, there is also a string buffer, which is basically an area of special purpose random access memory, semi-random access actually, but yeah, which is a string buffer of the length of 127 bytes or characters, actually that's bytes. And its only purpose is to store a string there. You can store one string in this buffer, and it's actually important because we will, there will be like some instructions related to that. So keep in mind that apart from all the registers, there's also one buffer for a string, which is at most this size, and there's a set of different instructions which are doing operations on this buffer. Quite high level operations at that. Like, apart from x86, I don't think I ever saw such high level operations, but yeah. Well, even on x86, to be honest, I didn't. Cool. So now let's see what our disassembler currently writes. I believe I was using Python 3 and it was called this. Okay, and it outputs something. It basically goes through all the functions and outputs them. And we did analyze the small ones. For example, this one sets the 127 register. I think we established later that this is the code basically tries to create a stack from the register bank, and which means that this 127 points at the stack, and or rather it's the stack register, and it's initialized by some default value at the beginning, which would be this one, I believe, and then it's being moved up and down with pushes or pops. So this is basically a stack pointer, this 127. And this is the main function, slot 0, as we saw in the Arduino code, but start slot is slot 0, so this is the first function which is called. And it sets something to, like, sets this SP to this register at the beginning, so this is like where the stack begins. And then it calls the function number 2, which is this function, or rather function not number 2, but function starting at slot 2. Again, one slot, 4 bytes, but the function can obviously take more than 4 bytes. It takes next slots. So here, for example, the length is 7. 1, 2, 3, 4, 5, 67, plus there is 1 byte of length at the beginning, so that's 8 bytes, 2 slots. Therefore, next function is obviously starts at the slot 2, where this one started at slot 0. And yeah, so this is the another main function. We have not yet analyzed it, and it's pretty long, as you can see. I don't believe we analyzed this function 31 either. It's pretty long again. We didn't analyze function number 58 either, because again it's long, so this is what we'll be doing today. We did analyze these functions though. And sorry. This function is, we determined that it's push. As you can see, the first something is written, what probably is in the register A is written into the register number which is present in R127, which we determined is stack pointer, and then it increases the linc, like long increase this stack pointer. So it's a stack which is growing downwards. It's not like on x86, it's growing in the other direction than on x86. Then we decided that this is actually pop, and it puts the, I think in the 0 register, it puts the value which it popped in the 0 register. I think so, at least. And then I don't think we looked at this function yet. We can take a look at it in a second. We did take a look at these two functions. And what we determined is that these two functions are actually creating dynamically a new function in the EEPROM slot, which is in the last EEPROM slot. Like at the, this is EEPROM, and all the functions are at the beginning, which we are looking at, then this is actually writing a function which is at the end of the EEPROM. And it's writing this function. And we determined that this is actually writing, this is like a workaround for the CPU, because this CPU, this FPU actually, cannot, it cannot read or write from addresses or to addresses in EEPROM which are stored in the register. So if you put in register 10 because like value 10, because you want to read something from EEPROM slot 10, you cannot do it because there is no instruction to do that. You have to like hard code the actual slot name in the EEPROM. So that means that if somebody isn't really sure which EEPROM do they want to read from or write to actually, and they calculate it at runtime, this is what they have to do. The problem is here that this instruction takes about 1000 cycles. This is super slow, but whatever. And it also, the EEPROM isn't like the greatest here, I believe. It's like each cell can be written 100,000 times or 10,000 times. So yeah, this code wouldn't work for too long. Now, yeah, so this is either reading or writing. I don't know, with the 3 here, this is the 3, is the length of the function, and this is the function itself. So it's db0080, 80 is the return, which means it's db00, which we can look here at db. What is db? And db is, yeah, save. So this is writing, and then dd is loading. Which means that, yeah, so this function A9 writes to EEPROM, and then we have dd, the function B0, and this is what loads from the EEPROM. And so we know when these two functions would be used, we either are going to store some data, hopefully, to EEPROM and load the data later, to use EEPROM as a super slow random access memory, or, which is more probable, this is for self-modifying code. So we will have to deal with self-modifying code. And yeah, I'm actually going to take a look if I have made any notes. I didn't take any notes last time, so let me take a quickly fix that. A9 is probably like write 4 bytes to EEPROM, and BO is no, sorry, that's the other way around, or is it like this? DB is like this. Load or read 4 bytes from EEPROM. Now what I'm interested in is which registers hold the values. This is where the address is going, and okay, it's this, so R2 and R1. Yeah, R1 probably has the value which is supposed to be written, and yeah, I think that's it. So R1 is going to be what to write? Which value is shifted? It shifts from R2, it puts this in R2, and then it selects R16. So it shifts R16 by R2. I'm getting confused here. Then it does this, and then, okay, whichever is selected. I guess we will see how it's being called. 3010 select shift R2. Yeah, because it grabs the address where it wants to write. It is in R2 register, and then it shifts the R2 register by 10 times left, which means it will get it on this position, and then it ORs it to this position. And then it selects R1. No, it selects R... Okay, so it's wrong, what I said. Okay, no, it's not R2. It's R16 and R17, so that's fine now. R16, this is the address, and this, and R17. I'm getting confused by this architecture, honestly. And this is like 4 bytes, which are to be written there, which means probably here only R16 is being used for the address. Let me double check it. Yeah, it only uses R16. Perfect. So we have these two functions. Then I said that above we had push and pop. So 90 is push and 92 is pop. And probably the return value is in R0. I think that's R0. Else set 0. What does this do? Else set 0. Set register A from register 0. Oh, so no, it returns in register A. Register A is from, yeah, it sets both actually. And if we push something, I'm also guessing that the value which is going to be pushed to the stack is just going to be in the A register. Let's see what save int does. Save int puts, yeah, register A to whatever register is pointed by to a register, which is to the value, to the register which number is in another register. Okay. Perfect. So this means that here it's A is what, like the value. Cool. So we have these two functions already analyzed. Do note that it might disassemble other functions wrongly because we have not yet completed our disassembler. And our disassembler, by the way, which I have not opened yet, looks like this. This is our disassembler. It's pretty short actually, apart from the opcode definition. So we will continue with that. Please make tutorial videos from KrzaQ. I would love to, but I just do not have time to make videos. That's why I am live streaming, because live streaming takes way less time. Again, if you have any questions, you have to ping KrzaQ, who is today's moderator. Perfect. Now, let's analyze this function, because in the end, the idea is not to complete the disassembler, is to analyze the function. And if any code starts looking really weird, that means we have to like append and fix the opcodes here. Cool. So, okay, select A a call. Okay, so it just like starts by calling some function. Function 90. So okay, function 90 was push. So it just pushes something to the stack. Where did I put it? Let's put it here. Okay, it pushes register 24 to the stack, register 25 to the stack, and register 26 to the stack. This looks like preserving values, because it's probably going to clubber the values in the registers, like just, you know, scramble them, write over them, use these registers for something else, so it has to preserve them on the stack. And if everything works correctly with our disassembler, we should see calls to pop at the end of a function to get the values to these registers in the reverse order, so we can take a look. Yeah, it's here. So yeah, it like pops value into register 26, 25, and 24, and then returns. So we know this is preserving registers, this is fine. Then we have select this, and it sets register 1 to the value FE. Register 1. I'm just going to make sure that lset I is actually setting the register register A. Yeah, it sets register A to the long. Oh, it just takes one argument, which is a byte. I think we have it correctly implemented here. Yeah, we have it correctly implemented. That's fine. Since I don't remember which opcodes we had implemented and which we didn't, I'm going to be double checking that. Selects this and then shifts it. I know we have this implemented. If it has an argument, we have it implemented. That's basically the rule. If it doesn't have any arguments like this ones, they might not be implemented. Because only the registers only the opcodes which we implemented in the disassembler fully have any arguments which show up for them. Okay, so it put this FE, then it selects register 18 and it shifts it by 1. I have no idea what's in register 18. Then it selects register 17 and it increments it, shifts it, and selects register 16. These are the input registers probably. As we saw in the two other functions for modifying the EEPROM, the input values were in this R16, R17 registers, so I'm extrapolating and assuming that R18 is also going to be a register used for passing arguments. So these are arguments which are being passed here. Okay, then ladd. What is ladd? What arguments does it have? Because it might not be implemented. Okay. It's just ladd, right? Not li. Here we go. It actually takes a registry number and it adds whatever registry is to the value, the long integer value. Okay, so it's a long integer add. Because again, this is an FPU, so a normal add would probably add floating point values. We do have to write this though. So ladd, here we go, and we need to put a register number, which is regnum. Perfect. Okay, and we do have to restart the disassembler and redisassemble this again, because otherwise all the instructions after that would be corrupted. As in, well, not all of them, they might synchronize automatically, but at some point by accident. But apart from that, we need to do that. So it adds to this the input, and then it selects this and does lset. And lset again probably needs this register here. Yeah, there is this register, this NN here. This is the register number, so we need to put regnum again. Okay, what I'm doing currently is basically I'm fixing the disassembler before I can analyze the code. Then we have the copy instruction. I do not believe we have it implemented either. Copy instruction takes 2 registers, so we need to give it 2 registers. And copy looks like a move instruction in other assemblers. Okay. Regnum. I'm just adding the parameters basically here to each instruction. Cool. So we had the, okay, so it's copies. I don't understand which direction is it copying. Okay, so this is the source register and this is the destination register, sorry. So this is the source register and it's being copied here into the destination register. So 16 is copied to 25, 19 is copied to 26, and 25 is copied to 16. Well, this is weird. Why is it like that? Like we just copied it here, why is it copied back? I don't know, maybe it will be clear later on. Then we call BO, and BO is, it reads 4 bytes from EEPROM. Okay, then there's XOR, yay, there's an XOR alert. Cyber anomaly detected. If we see XOR somewhere, there's something weird is going on. XOR is really rarely used for anything, apart from zeroing values or doing some kind of weird encryption. So it's XORing whatever it got read from the EEPROM, and it's XORing it with whatever is in R26, which is R19, which is, I guess, the input parameter. So this function takes at least 4 arguments, it seems, and the last one is whatever value is being XORed here with. Then it copies the output to R17, R25 again. I don't get it. Why is it doing that? But maybe this will be obvious later on. And then it calls A9. What is A9? A9 is write 4 bytes to EEPROM. So this looks like it's grabbing something from the EEPROM and then it's XORing it with something, with the 4th parameter, which is in R19. And then let me guess, there's going to be a loop. It increments 25, this is probably the slot number, and lose CMP, I do not have this implemented. What is this? CMP2. It takes 2 arguments and it basically does this, and it sets the register. Oh, by the way, there is this bit, like this status register, which is basically a flag register. And comparing or jumps will work in a pretty weird way on this architecture, but we will get there in a second. Let me just add this so we can fix it. It takes 2 regnums, 2 register numbers. Cool, we can fix it. And we were here. Okay, so it compares these 2 registers. So 24, whatever is in 24, but has to be the end address. And this is the slot number. The slot number is passed to the argument. Oh, okay, it's doing this because it's actually copying it to the argument register, and the argument register might be clobbered in the callee. That makes sense. This is probably the calling convention used here. And then it does jump CC. Jump CC, sorry, GMP CC. There's no GMP CC. Perfect. There's just GMP. Okay, this is unconditional jump, and we have CC, so that probably means it's just a conditional jump. This is a test condition, which is 1 byte, and then we have BB, which is 2 bytes, it seems, is the function address. Now this is quite funny because it jumps into a place in the function which is addressed not by slot number, because then you could do only jumps inside, like, you know, to areas which are aligned by 4, but it jumps to the address which is counted from the beginning of the function, which is quite weird, quite unusual. It's not an EEPROM address, it's a function address. It's same like in Python. Basically, if you know Python bytecode, it's really similar here. But it's different when it's in x86. So what we have to do is we have to... Why does it say that there are 2 bytes? I do not believe that there are 2 bytes. Oh no, because the functions in Flash can be larger. Okay, that's fine. Because here in EEPROM, the functions are limited to be 256 bytes. So I was thinking like, okay, why do you need in that case for the value to be larger than 1 byte? But I guess in the flash memory of the FPU, they can be larger. So jump CC, and then it takes the condition byte, which is, we are going to talk about it in a second, and then the U16, which is the address actually in the function. So let's take a look where it's jumping. is jumping to address 50 in this function, and I think we are already looking here. So address 50, I'm not sure this is actually, no, wait. We don't have this implemented. Why is there only one argument where we actually put two arguments here, right? Because this is not implemented, so we need to implement this now. Yeah, it's not implemented. We have the 32-bit version implemented, but we don't have the 16 version implemented, so we have to do this. And it's a 16-bit version, so we do not need these, but we do need to fix this. This is no, this is I, and this is I+1. This is big endian, remember that, and we add 2. Okay. And here we have to fix it to 4. No. Here. Okay, perfect. Okay, now 2A is the address where it's jumping. Let's take a look. So it's jumping to A here, which might make sense. It might actually make sense for it to jump here, because here it's still some, it might actually explain why, you know, I was wondering, why does it copy R16 to R25 just to copy it back? If it's in a loop, that makes a lot of sense, so I'm actually convinced that the jump is jumping here. And then there is this condition here. The condition is quite funny. It's actually split into 4 bits. So there is the mask and there is the value. And what it actually does, it grabs the 4 lower bits of the status register. So it does, so the let's go just S, and it does them. Oh, I do not have. No, it does. Sorry, let me maybe clear the screen. Okay, status register and mask has to be equal to value. If this is met, this condition is met, then we have a jump. In this case, the mask is the top nibble, meaning 5, this is the mask, and the value, this is the lower nibble, which is 0. So that means that in our case, S and 5, which is like this, has to be equal to 0. Now, if we look at the status register, we can check which bits are we interested in, and then so status register. Yeah, here we go. These are the lower 4 bits, and we are interested in this bit and this bit. So Z and I. I is for infinity. I don't think that matters at all for comparisons between longs. It would matter for comparisons between floating points. So we basically check only for 0, and the 0 has to be the 0 flag has to be set to 0, which means it was not 0, I believe. So this jump should be understood as where's the jump? Here, as basically jump not equal or jump not 0. While it's not equal, jump to this address, to A. This is how it would look in, or rather, jump and E, and the address, this is how it would look on x86. That's a pretty weird architecture, actually, to do it like this between mask and value. It's pretty cool, actually. Pretty cool because it's pretty weird. Cool. So there's a jump, and then when the jump doesn't take place, like there is no jump, we finished the loop, then we restore the registers and return. So what this function does is, again, it XORs something in memory, where 24 is the, sorry, 94. So 94, this is the function, and it like XOR EEPROM, basically. There are some arguments, I do not know what the arguments are. Apart from R19, I know that R19 is the XOR key. We might want to take a look at what is actually, how is it called. So we know this is the key, 4-byte key. We can take a quick look. For example, here, R16. Is there anything weird done with R16? It yeah, it does some weird stuff with it, so I'm not going to try to figure out what it does. I'm guessing one of this is going to be the address, one of these is going to be the size, and I don't know why there's another one actually. And the address might be either in bytes or it might be in like slot addresses, like, you know, 4 bytes. I don't know. I'm not going to analyze it or look at it too much. What I'm going to do, I'm going to basically look how this function is called to try to determine it. 5 isn't, oh right, sorry, 5 obviously. That would be 9, my bad. Obviously 5 is like this. Sorry about that. So we can take a look again at the here, there's n, none. Okay, so that makes sense as well, only for floats. These 2 bits are only for floats. Sorry about that. Perfect. Now we have 5 functions analyzed, and we do not have analyzed these longer functions. They are not analyzed for us yet. I guess we can go here and try to analyze it. What I would like to find pretty quick is I would like to find any calls to the XOR function to know what is XORed. Are these the slots of the functions, the addresses of the functions? Should we XOR something in the disassembly before we continue, or is it some data in the EEPROM? Okay, which function is the smallest maybe? Okay, all of them seems rather large. So let's just go with I think 31, sorry, I think this one is the smallest. Yeah, 31 is the smallest, so let's go with it. Let's go with this one. Okay, select MA. Do we have select MA implemented? I do not believe we have select MA. This is a select matrix A. Okay, so there are, I think, 3 more matrix registers, and these work as, these are like MA, MB, and MC. And a matrix is basically a set of general purpose registers starting at a given register and going through like a number of registers. So for example, R30, R31, R32, and so on, of a given size, and it's a 2D matrix. So basically, if here we would pass, this is the register number, like for example 10, which would mean R10, like register number 10, and then 2 and 2, meaning it would be a matrix like an array of 2 cells by 2 cells. Then the matrix would start at R10, then go to R11, R12, and R13, like 4 registers, right? Because 2 by 2. And this would be the first row, and this would be the second row. So this is like as similar as the C language as it gets. And it takes 3 registers, 3 arguments. We basically have to look for select MA and put that here. So first there's this register number, and then we have 2 bytes saying of what's the size of the matrix. I wonder if there's a limitation of if we could do some funky stuff here. Okay, let's disassemble it. I would actually like to change our disassembler to only disassemble the 31 function, so we don't have this much stuff here on the screen. We are going through all the functions, but if the function slot is not equal to 31, is it hexadecimal? It is hexadecimal, so OX. Then continue. I want to only display this one function. Okay, that's better. Select NB, I should actually have copied this already. Here we go, and here we go. You know what I'm going to do is here, clear, this is Linux. Okay. And then there's mop. Mop, as I said, is basically a matrix operation. So this is an extension. If you look at more advanced VMs or CPUs or whatever, more advanced, more like with a larger instruction set, then they usually the opcode table, like this is the opcode table, and each entry here, each byte here is one opcode, right? There might be some bytes which are basically aren't opcodes themselves, but rather they point at like another table, and the idea is to read another byte and look at that byte, and there are another instruction here. And that's pretty common for x86, and it's common to this architecture as well. And MOP and FFT are such extension opcodes, basically, that they require you to read another byte, and from that byte you will know what opcode that is. So MOP, we have MOP here, and then, which means we need to switch our disassembler to read this table here, this MOPs table, which is the extension table. We already have it here. Now I would actually love to do something like this. Okay, yeah. Okay, that way I will be able to reuse the code which I have already here. Now we have disassemble, we have this, and it got opcode this. Now, how do we do it in a way that we don't write too much code? Opcode, okay, so mnemonic. If mnemonic is equal to, sorry, it's going to be a string, right? Yeah, so if it's mop, in that case, we need to read another, we need to read another opcode. An opcode, in this case, is going to be not opcodes, but mops from another table. Get opcode, and otherwise we don't know, but like matrix operation, but we don't know what is it. Okay, and then we can continue going through the arguments, because the arguments are going to be the same. And here, yeah, that's fine. We can work with that. So it's mop and it's 19, and that didn't work too well. Why? Oh, because I forgot to do mnem opcode 0. Okay, here we go. Okay, perfect. mx copy ab. How do you exit this namespace? You don't. It's just for one instruction, basically. So every instruction with a prefix xe, with a prefix 6e is taken from the mop table. But if you do not have this 6e prefix, then you just use the normal table. It's basically like similar, like with some instructions on x86, like most FPU instructions on x86, I think, have a prefix as well. Cool. So yeah, you can think of 6e as a prefix for mop instructions. And this is like mx copy ab. Does this take any arguments? We do not have it here because we have this other document with these instructions, and it's not here either because it's probably under the name copy ab. Yeah, it's just matrix copy one matrix to the other matrix. So you have two matrices and it's just a copy. You can think of it either as copying matrix to matrix, or you can think about it as like memcopy. Like copy a set of registers to another set of registers, just with one operation like that. It doesn't have to be a matrix operation in this case. And I think that's actually what's going on here, because it's like a matrix of 8 registers in a row, and it just grabs the registers from here and puts them here, and that's it. It doesn't do anything. It probably won't do anything else with these matrices. Now there is the long U byte. So this is just like a fast register copy instead of doing select A, copy one register like 16 to 24, 17 to 25, and so on. This piece of code is here. Then we have long ubyte. Let's see what's long ubyte. Load register 0 with 8-bit unsigned value. Okay. What's the difference between this and like else set I? I don't know, but sorry, we just put the byte here. Okay. Long ubyte. No, not random. That's an immediate value 8-bit. Perfect. Then there's copy 0. I do not know what copy 0 is. We did handle. Oh, it's put register 0 to this. And what did it put the? Okay, it put 31, value 31 here. That's fine. We need register number to copy 0. Copy 0, that's a register number. Okay, and then there's long keyword. Okay, what's this? Load register 0 with. It's really good that we implemented. Yeah, we implemented the U16 because now it's going to be useful. And here it's a U word. What's the difference between? Oh, no. Wait. This is a signed word. But I'm going to leave it as is. I'm using hexadecimal values anyway, so I don't care. So this is fine, and I'm going to do the same here. Yeah. It should be S here, I know that, but I'm displaying hexadecimal values anyway. Cool. So it puts this value in this register, this value in this register, this value in this register. Selects this register and L sub. We do not have L sub. L sub takes a register number. Okay, so it basically subtracts a register by this. L sub by whatever register specify. Sub. Okay. So that's a register number. Wouldn't making use of the comments be easier? It might be. But I prefer to double check like both comments and documentation, just in case. I know some teams had problems with either documentation or the file being wrong. Okay. I do not believe we have L, right? Also, like, the comments aren't super helpful in case there are more than one parameter, because they do not specify what's the order. Okay, what is this L, right? It is a long, okay, it's most significant bit first, so this is big endian, puts into this register 32 by the value, that's fine. Yeah, for example here, write 32-bit long integer into this. You do not know if NN should be first, if it should be like second. It's better to double check it in the documentation. Otherwise, I would probably rely more on the comments. But so that's a good idea, but like just not doesn't always work. Okay. So it puts then this register here, and then it calls hello, welcome. This is doing some kind of an encryption, and this is the key. This is an XOR key. Now, the question is, 31. Does this ring a bell? 31. 2F. This is going to be the offset in the function, and this is going to be the size of the decryption, or a size of the end address. I don't know which one. Probably, I don't know which one. Yeah. 2F. 2F is this E, right? Here, so it starts from here and it does the XORing. Perfect. So we know this is self-modifying code. We know that all what is here is this is garbage. It's encrypted. We shouldn't look at it yet. We should decrypt it instead. And before we get there, oh, look what's going on here, by the way. It's again setting the registers, but copying in the second direction. So it's basically preserving the arguments of a function. Then it does the decryption of a function. Then it restores the arguments to a function, and then this knob is probably just, it's a real knob, that's my guess. Like real knob operation, that's just padding. Because again, we have operations on EEPROM which are 4 bytes aligned, right? So this has to pad, and this is 2F. 2F doesn't look like padded, right? Like 30 looks like a proper address, but do remember that before each function there's the length of the function, 1 byte, 1 more byte. So 2F is the address in the function, but you have to add 1 byte and you get the address in the EEPROM, like in bytes, and that would be 30. And 30 is divisible by 30. That's divisible by 4, which means you can address it in the EEPROM. So this is why the knob is here, to make sure that whatever else is there is actually divisible by 4 and can be worked with in EEPROM. Which I guess would mean that to this 2F we should find some add 1 or increment 1 in the 94 function if we look later at it. Here, 77, what might be the 77 here? Is it the end? It will be the end address, because the function is too short for it to be anything else. So we know this is the end address. Perfect. Which means that we can actually, we solved the mystery. This is the slot, like the, I don't know, EEPROM slot, or like the function. That's actually the function slot in EEPROM. R17 is the, no. Yeah, okay, that's fine. R17 is the start address in function. R18 is the end address in function. And the R19 is the key. So what we need to do now is we need to do the dexoring, add the dexoring to our disassembler. Otherwise, we will not be able to read this code, because this code is encrypted currently. That's why there are like these question marks here. Perfect. Now, how do we do that? Or rather, where do we do that? I guess we can do it. Who does the disassembling? Here we do the disassembling, so we do it here. If f slot is equal to 31, in that case we need to do the decryption. So decrypt f, and I will just hardcode it here. Like there are 3 functions which might be encrypted. There is no sense of making it automatic. It would just waste our time. And oh yeah, and the key. That's pretty important. Given that the key is here, that means that each function might have its own key. And now we need to actually implement the decrypt thing. So decrypt, then we have function, whatever f, then we have the slot, we have, we are not going to be using the slot because we are addressing the bytes inside the function. Start and key, okay. Now, how do we interact with it? Or rather, that's a byte array, right? That's a byte array, code, it's data, and data is a byte array on its own. That's good, that's really good. So, while I is start, I is less than this, but we add 4 each time. Now we grab 4 bytes, that would be f of, sorry, data code, what was it? It's code, okay. From start to start plus 4. Now we have to interpret it as little endian or big endian, I don't know. And then we have to write it back. So yeah, are we importing? Oh, okay. Yeah, okay. From struct import everything. I could just do this, but I'm lazy. I feel lazy. So D is unpack. I'm assuming it's big endian. So let's do it like this. D from 0. Then we XOR it, and then we need to pack it again. So pack the same, assuming it's a big endian. And D, okay. And then we need to put it back, and to put it back we basically do the reverse. And here we need to XOR it, so D XOR with key. And let's see if this actually gives us anything. We can, you know what, we can do another thing, print. To X key, X. Okay, and here we go with start and key. Okay, let's take a look. Did anything happen? I don't know. Doesn't look like this E right was here, right? The E, it was here. What's the key, by the way? The key, no, the key looks sane. What? Let me just comment this out. Yeah, this E right is here, so I did something incorrectly. Ooh, right, I. It should be I here. Thank you, Gabor, for noticing it. That would be funny. My bad, my bad. It's pretty weird it didn't work though. Like, at least on the E right. Okay, okay, that's better. Hello. At least I think it's better. I'm not sure if it's better. It doesn't look better. As in, what is going on here? What is going on here? No, it's not. Maybe the key is a little endian after all. Okay, let's take a look now. It's even worse. Or maybe no. Let's see. Select X. Maybe it actually is select X. Select X, select register. We do not have it in our opcodes. Okay. And right block. I think that's right block. Right multiple 32-bit. Hey, but that's actually might be correct. Oh, this is funny. Number of registers, sorry, number of values to write. And these are the values, and it's no, but that might be right. This looks correct. Well, okay, correct as far as statistically we can say, like on the looking at two opcodes, but we'll get it. So this is quite funny. It actually seems to be a for loop, which is supposed to fill multiple registers. This is really funny. Our block here. So we have like this. Let's just do it with one new thing, which does like, I don't know, like blk-im32. Let's do it like this, block 32 and a new type, blk u32. Let's call it 7. That's what, how was it called, right? M32, sorry, u32. Okay, and now we need to handle it here. Elif, you know what, I'm going to do an else here. I'm going to say here like race, it's race in Python, right? Unknown arc, or rather, sorry. And yeah, perfect, it works. So arc is this block BL key thingy. Now we need to get first the number of, they call it TC, right? The number of values, that's 1 byte. So that's D from I, and we add 1, and this is the number of values. And now to the mnemonic we add like the number of values, which is quite funny already. I'm going to do a decimal value, if you believe it or not. Probably don't believe it, but I'm going for this small value. Okay, and now for I in no, I would just shadow I, but that might be fine. But I actually need it for J. Is J used somewhere here? No, J is not used here. I can use J for J in that's Python 3. So range, sorry. Sorry about that. TC. We grab 4 bytes and we do this on them. But I'm not going to do that on them. Now we can do this. If I have it already implemented, then we can do this. We can do this, we can do this, and we can do this. Okay. Perfect. Yeah. Yeah. Oh, this is quite funny, but this is true. Like, this is a long opcode, but this is how write block works. And then it has like several values. How many values do we have? We have 16 values. Then there's a jump, and we do not have jump implemented. Where does jump jump? Jump jumps to 83, no. Jumps is not a conditional jump. It takes to, okay. So jump jumps to im. It's weird. Why do we have jump there? I do not understand that. It might be something wrong. But there's a jump. So we jump to 77. We jump over this and we exit. Okay, okay, this is cool. No, that's fine. That's fine. This just jumps to the end of the decrypted block, or rather after the decrypted block. So this whole decrypted block actually tried to conceal, to hide these constants. So these constants might be pretty interesting for us soon. So I'm going to note down these constants. There are 16 of them. And we might have some fun with them shortly. So is it block or is it bulk? It's a good question, Sopel. I don't know. I'm going to call it block, but let's say, what do they call it? Right, BLK. They call it okay, they don't call it anything. Yeah, it doesn't say either block or bulk. It might be both. Probably bulk. Cool. So we have this function analyzed. What this function does is just like sneaky load secret values. This is what this function does. Perfect. So if we have this function analyzed, then we have 2 more functions. Let me remove the... let me remove this. So we have this assembly of all the functions. And now we have 2 left. We have this 58 left, and we have this 24 left. Sorry, O2 left. Let's start with O2. So I'm going to replace this with O2. Okay, and then what's happening here? Oh, we do know this one. Then we do know this one. We do know what's going on here. We know this is again self-modifying code. So we have to decrypt it as well. Elif, this is the function O2. Then we decrypt it, and O2 is the first argument. Then 2f is 2f, same like here, and 97 is the end address, so this is slightly larger than the decryption code. Is different, as you can see, the decryption code is different. So yeah, we do this, and it should be decrypted. Perfect, now we start here. Read var. What is read var? I have no idea what is read var. Read var. Read internal variable. Okay, and it takes a byte, which is the index of an internal variable. So it looks like there are more registers like these registers, and they are related to like the settings of a matrix, or like where A and X registers are pointing and stuff like that. So let's see which internal register are they interested in. So read var, and that was 1 single byte, right? So they are interested in E. E, which is what, 14? Yeah, and that's 14 if anyone is wondering. Yeah. I'm sorry, my handwriting is trouble. 14. Current length of string buffer. As you remember, the flag is passed into the string buffer, so this grabs the length of the string buffer. Perfect. So here we grab, where does it read to? It reads to register 0. Okay. So we read the length of a string into 0, then we select A now points to 0, and then we do a comparison, lummmfpu. I do not believe we have this written down. It compares the A register with a byte, so we need to put a byte in it. So lummmfpu. Thank you, Quam. Quam says that great stream, thank you, and that need to get you on some games with Live again. Yeah, we did play with Live Overflow some Apex accidentally on the stream. Well, accidentally. He was streaming and wanted to take a break, and somehow we decided to just go and play some Apex. That was actually pretty fun. Yeah, we might do it again, but on the other hand, we got wrecked really hard. Like, we didn't win a single game. Perfect. So it's comparing, wait, it's, no, not random. We wanted a byte. Okay, so it's comparing it to 17. That's what, like, 20, well, we know it's 23, it showed 23. And otherwise, there's a bra CC, which is, the difference between bra and jump on this architecture is that bra is relative. So it gets a relative value where to jump, while jump is absolute. It jumps to an absolute address. But apart from that, it behaves like in a similar way. I do not remember if this is relative address from that instruction or from the next instruction. I do not remember. Okay, so bra cc, I'm going to create something called rel u8 or rather s8. And I'm going to do it in both cases, but here we also need the flag byte. Oh, come on. And the flag byte, it works like test condition, it works identically to jump CC. Hello, I want to know more about VM protections when you are on a perfect stream because we are just solving something like that. Where the flag is checked on a VM running on a PIC microcontroller, which claims to be an FPU, an external FPU. Cool. Now we need to implement this rel S8. I do not believe this is. Okay, let's do it here. For example, elif arg is this rel, then this would be fine apart from it being. We need to add the address of the next opcode, so we just need to add I. Do we need to add I or I plus 1? I don't know. Or do we need to add I minus 1? I don't know. I honestly don't know. So, but we do need to do this. Rel 8 is not defined because to define it we need to write it here. Rel. It doesn't matter. These are just arbitrary numbers here. Okay, so let's go here, and then we jump somewhere around 85. Like, take it with a grain of salt. It's +1 or +2 bytes because I'm not sure how is it addressed. So 85, it's yeah, it's somewhere at the end of a function. I'm sorry about that. Okay. Babadoc writes, I'm back after a long time. Hi. Yep, hi. Perfect. So if the flag is not the size, jump out. So we know the size of a flag, it's supposed to be 23 bytes, like OX17, right? 23, oh wow, I can almost write. 23 bytes, this is the length of a flag. We know that at the beginning of the end of a flag what it's supposed to look like, so it's supposed to be DRGNS, then opening, then whatever, and 23 characters, which means the internal is 16 characters. 16. Oh, how many magic values do we have? We have 16. Is there one per character, perhaps? Maybe it is. Anyway, let's take a 5-minute break. I will be right back. I need to get some more water or tea, and we can continue with this. I'm going to leave you with some music, and yeah, so 5-minute break. Which means I'm going to mute here and I'm going to turn on some music. Be right back. How do I can actually somehow, how do I write that I will be back in 5 minutes? It's like this. Be back in 5 minutes. I probably need some, yeah, I probably need some more fancy way to do it. See you in 5 minutes. Okay, so I'm back and we can get going. Again, if you have any questions, you have to ping KrzaQ on YouTube chat, on our Discord, on our IRC. Otherwise, I will might miss the question. Cool. So, what do we do now? We continue to analyze that function, that O2 function. And we were at, what did we see? Oh, here. Yeah, this is like treated with a grain of salt. Then we have this str cell thingy, which is what? What is it? Who are you? Str cell. It's set string selection point. N is the start of a selection, M is the length of a selection. I have absolutely no idea what was that. That's probably like if in the string buffer there are probably some registers saying this is the start of a string, this is the end of a string, or start of a selection, end of a selection. Let's see how it actually works. It takes 2 arguments, and these arguments are bytes. So string, so how many teams did solve it? That's an excellent question. Let me check how many teams did solve it. Here we go, and 9 solves, so not a lot. And difficulty medium, yeah, it's high. 400 points high, not 500 points high, but high. Okay. It is not an easy task, especially if you're newer to reverse engineering. It might be somewhat challenging. I'm not saying impossible. No, by no means. But challenging, yes. Cool. So this is like set some selection point. I have no idea what kind of selection point. Let's see what happens next. That might reveal something. Let's not try to understand this if we don't have to. From 0 to 6. So it sets the selection point at 0 and then 6. So 0 and 1, 2, 3, 4, 5, 6. Okay, so it selects the beginning of a flag. What does it do now? Does it remove it so that it only like this part is left, or what else does it do? So there's the string selection. There's actually string compare next. And how does string compare work on this architecture? So we need to go to the instruction set back again. And this is compare string with string selection. And this is something you do not see ever on any architectures which are implemented in Silicon, which is an opcode followed by an ASCII string, ASCII Z string. ASCII Z means like ASCII 0 terminated. So yeah, there's the 0 termination at the end. Which means we need to implement yet another type of argument because we do not have it. This is ASCII Z. ASCII Z is 65. Because again, it doesn't matter, like, it's arbitrary. We can, let's just implement it somewhere here after bulk maybe. If the argument is ASCII Z, then string is empty at the beginning. Oh my, this is going to be this is Python 3. You know what? This is my string. Better. How does appending to byte array work? No, okay, let's just go with this. This is my string. Now, while d.I is not equal to 0, we want to do append d.I and increment d.I. Now, if it's 0, we still need to increment it, but we do not append it to the string. And now we can do the string, it's a string from byte array, which is S, and we can say that this is like ASCII. Okay, and now for to the mnemonic, we can just add this, and this. Yes, perfect. Yes, better. So what do we compare it with? We compare it with, oh, Dragon sector. And if it's, I'm assuming this is like not correct, jump again to 85. Then we select the end of the flag. If this is not at the end of the flag, jump away. And this is another function which is not implemented. This code starts to make sense, which is really nice. And it starts to be relevant to the flag, not like some functions which are helper functions. Do you have quality assurance before pushing the challenges to the CTF? Yes. For Dragon CTF, the hard requirement is for the challenge to be tested by at least one other person than the author. This is a hard requirement. Our captain does not allow a challenge to be passed on the CTF if it hasn't been tested. That doesn't matter. We always push perfect challenges because sometimes even if we solve the challenge, it turns out that there's like a super simple solution which we just didn't spot, and that's what happened on the teaser, I believe, for one of the challenges. And yeah, but that happens, but that's fine, the challenge works. And with dynamic scoring system, that's actually not a big problem either. Okay, what does this do? Did I say while okay, I'm sorry. If I sometimes inject Polish words, I'm sorry. It's just like this hour or something. This is set field separator characters. This is a super high level function. The string specifies a list of characters, maximum of 6, to be used as field separators. What's a field separator? For example, if you have like values like this and you want to split them by like a comma in this case, that's like the comma is the field separator. It's sometimes called the delimiter character as well. Pretty obvious. So we need to, this is another ASCII Z, so it's really good that we have this ASCII Z implemented. strf char ASCII Z. Okay, and the delimiter is being set to these characters, so that means we are going to do a split over these characters. So this is going to be, I don't know, like group 0 or 1, I don't know how we can end group 1, and yeah. And I guess we are going to do the split because we want to get to this group, whatever that is. And this is string field, find field in string, which is the field number. And it's the selection point is set to the specified field. So we basically select, and I'm guessing this byte is going to be 0 is the start. Okay, so that's going to be 2 because they actually count from 1. They don't count from 0. Field is immediate value 8-bit. Sorry, here we go. Okay, yeah, we select the 16 bytes which are inside the flag. So that means we select this, whatever is here, this is being selected. And after we select it, we do like a 1, we set it to 28 for some reason, and the clear was a clear. I do not believe we have clear register. It sets the register to 0. We do not have this described fully. I always said implemented, but described is probably a better term. Did we? Yeah, I did. Okay, perfect. Okay, so we clear R2, we set this to 28. 28 is what? That's 40. 40 as in decimal 40. I don't know why we set this to 40, but we set it to 40, whatever. Then R0, we read var 11, we put 11 here, 11 hexadecimal, which is 17 decimal. Save index, so we put this into the register, we increment it twice, and we string ins to, what's the string ins? Increment string selection point, okay. So this, there's a loop probably. If R2, okay, so R2 here is set to 0 and here is checked against 16. R2 is our iterator register. And we increment it. R1 is, oh, read var 11, I know, or 17. We need to check this read var, like, yeah, here. Internal mode word, no, decimal, here. 17. 8-bit character at string selection point. So this reads one character which is at selection point. Okay, perfect. So here, and where does it read it? Sorry, it reads it to 0. Yeah, it reads it to register 0. Perfect. So we put in register 0 here the ASCII code of whatever character is at the beginning of the flag, so here. And then we, what do? We save it into whatever is at this address. And at this address is select a push, okay. So at R40, we push the flag character to R40. Then we increment it here. So the first flag character is going to be at R40, next one at R41, and so forth, 42, until we reach at the end R55. The last flag character is going to be here, or rather last character from like between the braces. Cool, and once we have it ready, so it jumps 5B here, yeah. Once we have all the characters put in to these registers, we call 58. Okay, and after we call 58, we have no idea what 58 is yet. We didn't analyze 58, we still don't know, like what is it, 58? We are analyzing this, this is like the main function, or rather like the actual main. Check flag call 58. Okay. And after it's being called, we compare the return value. I'm assuming R0 is the return value. It sounded like that in other functions, I think. And we jump to 85, or we set the string. We do *set. What does this *set do? *set, copy string to the buffer, and it's an ASCII Z, so it sets the string to something. *set to another ASCII value. Let's see what the ASCII value is. Oh, it sets it to well done, or it jumps here, I guess, and it sets it to wrong flag. So whatever the flag check is in this function, we like the flag is being checked in this function. This is what I'm pretty sure about right now. And here you just set the register. What's going on here? That's also a good question. Oh, and this is re-encrypting the function. So this is the end of the encrypted part of the function. Call the 58 function to verify the flag, and then whether 0 or 1 is returned, say well done or wrong flag into, like, put it in the string buffer, and then the string buffer, if we look on the code in Arduino, which I obviously already closed. Here, if we look here, then at the end it grabs the string, like print string length, it grabs the string from the FPU and sends it to the serial. So perfect. I guess we analyze this function. Yeah, it like checks start end of flag. Call this like put flag in R40 to R55, and then call this function, and then like set string buffer to well done, because this is the only thing we are interested in. Which means we need to go to this function and to analyze this function, and we're done. This is literally the last function which we do not have yet analyzed. It's 58, right? It was 58, I believe. Okay, and it even crashed. That's fine. We are going to fix it in a second. We do know this is, yeah, again, the function 58. We do know this. We do know that this means, or rather, to here, we do know that this is decrypt the function in memory, execute it, and then recrypt. So we just need to add decryption to the set of our ifs, which we have here. That's 58. And okay, what are the values which we need to transcribe. That's here. OX58, then 2F, then BB here, and this is the key to the decryption. Here we go. And we decrypted it, hopefully successfully. Hopefully there aren't too many instructions which we are not handling correctly left. I hope that's the case, but doesn't have to be the case though. So, 2F, we start at 2F. Call 31. 31. We did analyze it, but it's in my notes. Where are my notes? Sneaky loads secret values. It puts the secret values. I don't remember in which registers the secret values are put though. I didn't note it. So let me quickly switch here and we are going to check which registers these were. The 72. Okay, so the secret values are in 72. You know what? I'm going to put my notes here actually. That didn't work. In R72 and onwards. Up to R 87. Am I? Yeah, 87. Okay, that's fine. Because there are 16 values, right? So 16 registers. Cool. Let's go back here. We are disassembling and working on function number or function starting at the slot 58. Cool. Okay, we do not have this. What is this MX transpose thingy here doing? We know what this is, right? This is matrix transpose, but we do have to probably describe what this does, or at least which arguments it takes. Transpose. Yeah, it's a typical mathematical operation. There is, I guess, little magic here. And my question would be like, what registers does it take? Oh, it doesn't take any registers because it always transposes matrix A to matrix, sorry, MB to MA. And we have the MB, which is the input, set to the registers where the flag is. And it's actually, the flag is being split into 4x4, and then we transpose it. So we are basically like grabbing the flag and doing something like this with them. That's fine. Or actually like not doing like this. I think that's just like a mirror by the diagonal. Then we clear 0. What was clear 0? See, that's not in this set. Clear 0. It doesn't take any arguments and it sets register 0 to 0. Then we increment the register 0 to 3. Okay. And then we do scalar add, and scalar add has this like matrix operations prefix. If you are super lost, then you might want to actually start with last week's, the end of last week's live stream, where I started coding everything which I'm working on today. What is this scalar add? This is it. Okay, why? So what's the number of this operation? It's 1. So code is 1. That's here. Scalar add. To each and every each and every matrix cell, it adds the value. And the value which is being added is, I guess, 3. Because it's like adds the value from register 0, right? It also takes no arguments. Which means 3 is added. Now here's a funny thing. The scalar add works on FP on floats. On FPU on floats. This is an FPU, right? So a normal add is going to work on floats. Now here, this is not a float. This is free as like not a float. But since we have in the MA register, because this is operating on MA matrix, and we have in MA matrix the flag, so the flag would be like, let's assume the first character is A, right? That's hexadecimal, obviously. So that's like this. And this value interpreted as a floating point value is actually the denormalized value. And value 3 is also a denormalized value, so additions on two denormalized values, as long as the result is still denormalized, works as normal addition. It's something I didn't think the players will notice, and it wasn't supposed to be a trap. So this is just, assume this is just adding integer to integer. It's not the case, but assume it is. So we need to add 3 to all, like we grabbed the flag, we already transposed it in the matrix, like flipped it, and then we add 3 to everywhere. I guess I should start noting it. So here, check the flag. 1, transpose the flag, the input. In a 4x4 matrix, the second is add 3 value 3 to each letter. And then we have this. This just says these registers with these numbers. And after I do that, do I have to read this? Okay, what's going on here? We select our 9, we put 8 in it, we select this, put 10 in it, this 18 in it, and this R1, and put this value in it. Then we clear, like set R12 to 0, put 48 in this, then in R3, and we select R3 and we do mul. What does mul does? Well, we know it's multiplication, right? But what arguments does it take? It takes a register and it multiplies register A by the register. It's a long multiplication, not a float one. And it's the result is put in register A. Okay, so lmul, we need a regnum. Then we add, we end something, and then we load something from R1. What is R1 set to? It's set to this, 38. What's 38 in decimal? That's 56 decimal. 56 is the registers where, sneaky load. No, it's the output matrix. The output matrix was set to 56, yeah, here. So this is the output matrix. This is where the transposed stuff was put into. So it grabs the first register of that. It loads it. It selects the 0 register. It copies 0 register to these 3 values. And then it shifts these values by the numbers which are here, which is basically... Okay, so it... What does it do? It grabs some values. This looks like bit operations, actually. Like, you know what this looks like? It looks like... it looks like super similar to this code or the opposite of this code. Which is fine with me. Okay, then it copies it. Yeah, there are the shifts and the lore. Yeah, this is exactly like this is this code. This code implemented in this weird assembly. And then we XOR it with R3. What is R3? Where did we get R3 from? R3 is it's this value which was calculated based on R2, R4, and R5. And so yeah, this is like this value, which is multiplied, added, and so on, and we XOR it with the flag. Now, what do we XOR it with? We XOR it with okay, so let me get this straight. It grabs, like, for example, if our flag is like our input, right, is ABCD, it grabs the first character, only for first character, and it's like 41 hexadecimal, so we have like this. And what this code does, it translates this into this, like basically puts this character here, like this byte here, this byte here, and this byte here. This is what this code does. And then after doing it, it XORs it, like XOR with R3 register, where R3 is being calculated here. And after that was done, after that's done, what happens next? It lowers it with R0. Let me... Why does it... Oh, R0 is the result of this XOR. And then we lower it. This smells like constant time check. Like, if you want to do a constant time check, you basically set something like accumulator, let's call it to 0, and then in a loop you do a or equal, and like whatever you are checking, let's say like you're checking x of 0 XOR y of 0. Oh, sorry, I. Let's do like this. Yeah, and then at the end, if a is not 0, that means is like return false. Yeah. This is a constant time check. This in the loop for each I, and because if this would be equal, then you would get always 0 here, and 0 ORed with 0 is always 0. So at the end, if everything was equal, you get 0 in the result. Otherwise, if this is not equal, one of them is not equal to the other, well, both of them are not equal then you get a non-zero value, and if you OR a non-zero value with 0, or with some other 0, or with some other value, you will always get a non-zero value, always. That's how OR works, if you think about it. It's always like adding bits, adding set bits inside. It never removes bit which is already set. It never turns it to 0. So this looks like a constant check operation. I'm guessing that R12 is set to 0 at the beginning of a loop somewhere. Clear R12. Yeah, this is a constant time check. Which is perfect. We have almost everything we need. And after the constant time check, increments the counters, compares it to did we reach like the last register. If no, then go like somewhere there. Otherwise, it's, what does it do? Jump to BB. And this is recrypting. Yeah. So what it returns is returns the result of this check, and this check is super simple. We did note already what the check does. It transposes it, it adds the value, and then it does the XOR with like some. We will need to calculate this, which we are going to do. It selects R3, and then it multiplies it with, so it selects this, then it multiplies it by R2, which is this, and then it adds to it this, and then it does on everything which is here, it does this. And that's it. And then it does the like putting the byte of the flag into 4 bytes, which means that if we take this value and if we take the magical values which we have here, let's do just that. How lucky I actually like split them into 4 pieces. We should get the letters. We should get letters. And if we get letters, then we need to subtract 3 from each of them, and then we need to do an inverse transpose, which is the same thing, I think, as transpose. So I'm going to create flag.py. I'm going to copy this. This is obviously, and this was a mistake. Yeah, and this in Python, is it like this in Python? I think it's like this in Python, yeah. So value is this. Then we have like magics or like whatever flag. It's this. And we XOR each and every one of them. So for I in range 16, flag is to be exort flag of I is to be exort with V. Flag of I is to be minus equal 3, because we add 3, verse we minus 3 here. And the transpose is not yet done. I'm going to do the transpose in a second. For now, I'm going to print them. Oh, we can print them here, I guess. Print as hexadecimal values. It should be, each one should be the same. It should be like AB, 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 AB. With these values being ASCII, but it should be repeating pattern in each of them. Cool, and flag I. Did I? No, that's fine. Okay, Python 3 flag. And okay, we have a repeating pattern here, but I think I did the 3 somewhere. Should no, I think it's fine. I shouldn't do this. No, I shouldn't do this because I should do this on all of them. So I should subtract 3 on each of them. But it only works for the first one. It didn't work for the other ones, which means there's some more trickery going on, and we will find the trickery which is going on unless I failed with something really hard. Anyway, my point is that I should do this. 03, 03, 03, 03. Yeah. Okay. Now. Okay. Let's trace the trickery. What trickery is going on here? We do this operation and we have it in R3. The question is, are any of these like incremented or whatever? We XOR it with R3. Now the question is anything being done? R1 is incremented, R13 is incremented, but I do not see any I was starting to think whether like this value is big endian or little endian if I didn't break it, but if we get a correct value for one of them, that should be fine. Okay, so R3 is fine, this is fine. Do we do something else here? R3, we XOR it, and we XOR the result here with this. Wait, we select R3, we do this, we do this. Where do we get the magic values? Because there might be some other thing done with the magic value. Magic values were in the registers 72 to 72, that's what, 48? Yeah, that's 48, right? Hex 72, 48, yeah. So 48, I did see register 48 being used here. We set this to register 13, and register 13, where are you used? You are used here. You are used to... we load from you into RA, I believe. We load from you into R0, sorry. Then we select it and then we XOR it. Okay, so, and we XOR it with this. So no, there is no other thing done. Why doesn't it work? There is no other trickery here. I do not see other trickery, at least. Because where's the loop? The loop is going to around 71. And around 71 is around here. So it does call this code again. Yeah, what I'm expecting here is that they do actually something with one of these registers. They do the XOR here, right? But they do not. It's being stored in register A, and register A is set to R0. Then, like, these registers are not being used anywhere else. Yeah, we are so close to the flag. Did we calculate the value wrongly? But no, it doesn't look to be calculated incorrectly. We grab this. We select that. We multiply it by R2, which is this value. Now we calculated correctly. And furthermore, am I doing some outputting wrong, maybe? Or did we maybe read these values incorrectly in read block? I'm going to double check that. Or read bulk, or whatever you want to call it. It was the function number 31, so let's go back for a second to the function number 31. And here we have this write block, and this is where we got the values, right? And let's see if we got this write block. It uses this bulk, and this bulk does +1 here, +4 here. Does this, and this is big endian, that's what they said. So we grab this, and this, and we just add it. Well, this does look correct. There doesn't seem to be anything wrong with this code, and we do increment here, we do increment here. This looks correctish, I would say. And these values look pretty okay as well. I wonder if this like 1337 is an accident here. Okay, let's go back to, so I'm pretty sure this write block is okay. Let's go to 3058. I'm going to actually dump it to some file this time. 58. Okay, and I need this step before I can transpose the matrix. Unless there's some... No, this is long, right? Oh, yo, I know. This is funny. This is a negative value. So given that this is the negative value, I cannot do this in Python because I will get an incorrect result. I have to change this to positive value. Okay. How do you do that? Can I just do like this and +1? I think this should be enough. Minus, thank you Python, but you are correct. This is the value I want. Now, well, is it? Unsupported string. Okay. Wow, this is a funny. Okay, but let's say. So A is this, and we put A here because this is a negative number. So we put this is minus actually here, and we put it here because the result will be slightly different. That might be this error. Did it help with anything? It didn't help with anything. Does it actually give the same result? I'm curious now. Or did I calculate it incorrectly? Let's just do... I'm going to double check if I calculated it maybe incorrectly. So give me this and do import struct unpack I and the value, which is a byte array of this byte, this byte, this byte, and this, no wait, this is the wrong value. This, did I get the value? Here, A5, okay. A5, okay. Why does it say that it's a... Oh, okay, so this is good. No, we did get it correctly. So if we get it correctly, something else that they do here, some overflow here. Isn't it a recalculating? Well, oh, so you're saying that... okay. Thank you, Panda, Quack Panda. I'm sorry if you butchered your name, but it is recalculating every time. Which means, which one of these is R3? R3 is the value, this one. Okay. So this is R3, this is R3. Okay. Yeah, it is recalculating it every time. I was looking at it, but I was looking at it from, like, let's say, a wrong direction. Okay, this doesn't work because we call it wrongly. Let's go to R3. Yeah, okay. Yeah, thank you, Panda. Now it's fine. Now we grab the bottom bits and we do a transpose on it. So we grab just the bottom bit and we put it in this is already in a matrix. Let's do a print here. Print CHR of X for X in flag 1. Okay, let's start with flag. Okay, and this is scrambled still because we need to do the matrix transpose. So the transpose is like this. J in range 4 for I in range 4, and we create a flag 1 flag output, I don't know, like good, of which is a byte array of 16, and like the destination index is I times 4 plus Y, the source index is J times 4 plus Y, so it's flipped, transposed, and good of destination I is flag of source I. And we actually need to print good. Yeah, flag pawning unit, that's the flag. Flag pawning unit, or like FPU, if you will. That's it. Obviously, like the flag has at the beginning and at the end the Dragon's stuff, so we can put it in our notes. Here. And this is the correct flag for this task, which I am going to enter. Am I going to enter? Can I? Yeah. Submit. Correct flag. Perfect. It didn't mark it as solved because it's after the CTF, but it's a correct flag. So there we have it. We are finished, or rather we have finished. and I'm going to upload my code to GitHub now. Thank you for being here and bearing this with me. Now, this challenge is actually open sourced already on my GitHub. So if you go to my GitHub, which is github/Gynvael, and you go to repositories and there's something like random stuff. Yeah, random stuff. Then there is the teaser Dragon CTF 2019 and ummmfpu. And yeah, this is how it looked connected to Arduino. And if we look at the source, you will find a really bad compiler assembler. I actually had to, well, I didn't have to write my own, no, I did have to write my own assembler for it. So yeah, I basically write my own assembler for it, and the assembler is so hacky, and I thought I could like get away with doing basically what I wanted to do is I wanted to take the assembly code and quickly, using some simple regular expression stuff like regular expressions, basically like string processing, change it into Python code. And that worked to an extent actually really well. Yeah, as you can see, like run as Python code, I do some string operations and then I run it as Python code. I compile it and I like execute it. But it's still required like to write a linker, to write like the encryption and so on. You can take a look how it looks like. The actual task, now this is the checker for the flag, or rather like how it was calculated. The actual task is in the task PY, and this is how, well, yeah, the encrypted code function, which is, this is the prologue, then it calls recrypt function, and then this is the epilogue. Yeah, I used like weird signs here as well. The actual code for the main function, for example, is like this. This is encrypted code and the main function, and it was later passed on to the linker, which, you know, compiled it, encrypted it, and then slotted it, put the functions in the bytecode in the random slots, well, proper slots in the EEPROM, and then created an image out of it. And yeah, this is how it looked like just jump, compare, jump, and in the end is call verify flag, which is the function which we look at load magics. It's encrypted code and it's just this, as we saw. And then verify flag was what we were. Yeah, this is LCG. It was LCG. Okay, almost identical as glibc. Oh my, I actually thought this is just calculating a constant value when I was solving it. Now I forgot I made the LCG here. LCG is like a super simple random number generator. Or it could be used to like in stream ciphers like here. And yeah, and we exert the flag. We iterate, yeah, this is what I did forget. And that's it. So I'm going to, I guess, give you a link to the repository. Thank you for being here with me today. If you speak Polish, tomorrow there's going to be a live stream, which is going to be the continuation of last week's topics. If you don't speak Polish, see you next week. And I have no idea what the topic is going to be. We'll figure out something. And I guess that's it for today. So thank you to my moderator KrzaQ, who helped me today. And thank you for being here. I wish you a pleasant evening or pleasant day wherever you are. And see you next week. I'm going to leave you with some music. So yeah, that's it. Bye-bye. Thank you.